Good afternoon, everyone. So I am Jaya Gupta, and today we are going to discuss the concepts of object detection, right? So object detection is actually one of the fields of this computer vision, one of the tasks we do under computer vision, right? So there are many algorithms came for object detection task. But still, there are some things people are usually kind of confused with the object detection, localization, segmentation, like instance segmentation. So here in this discussion, we are going to learn what is the difference between all of these concepts, and I will majorly focus on object detection, right? And I'll focus on the approach of this region based convolutional neural networks, right? There are some other approaches available, so I'll discuss other approaches in the coming sessions in this series. Fine, so let me share my slide now so that we'll start the discussion. So there is also hands-on on this approach of RCNN. We'll be doing after understanding the basic differences between the concepts of object detection, classification, segmentation, and all. Right. So welcome to you all in this session. So this is a profile about me. So currently I'm doing a PhD in computer science and engineering discipline. I did masters and bachelor's in this discipline only, and had like 8+ years of teaching as well as research experience in this field, qualified gate net etc, and also nvidia dli university ambassador, so that I got the opportunity to spread the knowledge about deep learning and computer vision practices in the eminent universities in india and some of the government um, like their institutions like icmr and cmri. Yes, someone is asking something. I think किसी का mic on है, so please off your mic. Yes. So yeah, let me proceed now with the field of computer vision. So basically, computer vision is a field where methods which help a camera to see what is inside an image, right? Because if we know that how our retina works, how we can see the object. So in that case, computer actually doesn't see like we see. We have retina and the things are processed by our mind, but in computer the computer actually see the pixels in the image, or we can say intensity values, right? So earlier we used to have such images which are very low resolution from our cameras. We click those images, and when we open those images in any paint or any image viewer software, then we see that there are small blocks we can see in image, and those blocks are actually the intensity values. Actually, I've covered all these things in the previous sessions, right? So right now I'm focusing on the classification, object detection, and other things. Classification I'll just touch, and then we'll majorly focus on object detection, right? So let's focus on the applications of computer vision where these approaches are applicable, right? So nowadays, we see that it is applied in agriculture, recognition, character recognition, OCRs, and face recognition, as well as this process control and all. Right? It is also applicable in geoscience, in face detection, right? In this remote sensing, so pollution control, autonomous cars and vehicles, industry quality inspection, right? So all these areas, biometrics, and also in medical imaging. So this computer vision technique is applicable in every domain nowadays where we can click a photograph, and if a camera can see the photograph and can understand what is there inside the image, it is able to process those things, and then our task becomes a lot more simpler, right? So now we have seen where these computer vision techniques are applicable. Now let's see what are different computer vision techniques we will encounter during this session, and what are the various applications available. So one is image classification. So you have seen like dog and cat classification. If you have a bit knowledge of computer vision, then people have might watch this thing. This is also not actually limited to dog and cat. It is applicable for breast cancer, or like breast cancer detection, whether the cancer is a malignant or is benign, right? Spam or not spam, right? So even in various robots where which are actually, or we can say drones, uh, we can use this image classification algorithm to see like this is the crop area and this is not, right? So this is the basic segregation of the whole field a drone can do, right? So this is really very much applicable in various domains to segregate the basic things. Then we have object detection. Then there is object tracking, semantic segmentation, and instance segmentation. So let's see the examples of all the things one by one. So image classification, as I already told you, that we have spam and not spam kind of things inside image classification. So there we have input as an image and output is a label, right? Whether it is a spam or not. In a similar way, we have multiple things in here, like some input variables. So now the vegetables and groceries are two different labels we can consider for this data set. Right? And also we have this is the simplest example we have seen already for image classification at various sources, right? If you have explored this field. Now let's see what is image classification. It works on a set of algorithms that maps the input data to a specific category. So the specific category is the label we are talking about right now. So in an image, there can be one label or there can be multiple labels. So there is one activation function. I'm directly jumping on activation functions. Why? Because if we'll put the activation function at the output layer just before the output, so the activation function, if sigmoid, it means that goes from 0 to 1, right? So 0 to 1 means there are two classes like dog or not dog, right? Cat, not cat, like this. Right. If there are more than one kind of things in there, then we can apply softmax as well on the for the activation function. So it will provide you the aggregate a distribution of probability scores. So that is what is applicable for image classification. So image classification can be done using machine learning as well as deep learning techniques, right? So some machine learning techniques are listed in here. So logistic regression, naive-based classifier, SGD means stochastic gradient classifier, k-nearest neighbors, decision trees, random forest, and support vector machines. So, like if you have explored sklearn, there are the very simple applications of all of these image classification techniques. So I'm not covering the hands-on of this technique in this scenario. So in this session, if you want me to cover, please message me so that I'll cover, because the things are ready with me, right? So I can cover later in the other session. Other than this, we can also apply convolutional neural networks for this image classification task. That can be implemented with Keras or TensorFlow. In Keras, we have multiple models available. Even we have pre-trained models like VGG19 and LexNet, VNet, and some other ResNet. There are many models available which are able to do the image classification task, right? So in those advanced models, there are multiple categories available, like 1,000 image categories are available with the ImageNet dataset, right? So it can be done using machine learning as well as deep learning, right? So now let's move to object. Yeah, that I'll do in the next session if you want me to cover. So let's move to object localization. Before going to object detection, there is one thing called object localization. So right now we have in our cameras, there is a boundary kind of thing comes when we try to pick a photograph, right? That boundary is actually the localization thing. It's not object detection, right? It is actually specifically localization. Why it is localization? Because it actually takes the coordinates x, y, as well as width and height of the rectangular box to see what is inside the image. Right. So it is actually a regression problem where output is x and y coordinates around the object of interest to draw bounding boxes, right? Input is an image, or we can say a real-time feed of a camera, or output is the x, y, and height and width of that rectangle, right? Object of interest or ROI, you can say, reason of interest. So next, we'll move to, okay, I have put an example in here. Like here is a bounding box around the face of the dog. So we have already can relate with our camera. Right. Now let's move to object detection. So object detection is actually more than object localization, right? So let's see what it is. So it has the bounding box, and along with it, we have the category of that bounding box, right? So in classification, we actually classify the whole image, right? But and the images are mostly there is one or two objects in the image of the same category, right? Usually for the image classification data sets. But in object detection, we have a lot more categories in a single image during training. Right. So there is a one person, white, like dog, and many things. More than one person can be there. Right. So that is object detection. One example is this also. So we have bounding box as well as the name of the object, or we can say category of that object. And this is on the real-time camera feed. So we have already seen these kind of examples if you are working currently in this field of computer vision. So there are a lot more examples available over the internet where this kind of camera feeds are able to track what are there, what the objects are there. So it is also very helpful in autonomous cars, right? So let's proceed and see what is actually object detection. So it is a computer vision techniques for locating instances of objects in an images or videos. Locating instances of objects means we are locating as well as classifying. So in short, we can say that object detection is image classification plus object localization, right? So we do both the things in object detection. The input is an image and output is actually the height and width as well as XY coordinates around all the object of interest along with the classes. So this line along with the classes is an add-on after object localization, right? That's why we combine both the concepts in here. So now let's see object detection hands-on, right? So first we will see the notebook. I've prepared a collab notebook for this. So here we have, let's see what is the data set we have. Like we have airplanes and its annotations. So annotations are available in CSV and what is there in it. Let's see that too. So in the annotations, we have a number here and some numbers here, right? So if you can relate, then this 10 is actually the number of objects available in the image. And this is actually the XY as well as height and width of rectangular boxes available. So this is inside our data set, using which we are going to train our algorithm, right? So this is planes 12. So in this dataset, this is actually a custom dataset where I've taken the images of airplanes only. There are not multiple objects because to cover everything inside the session, I've taken a smaller dataset, right? So we can also refer the COCO as well as VOC datasets. So for the actual implementation, like complete implementation. Right, this is the annotations. And if I look at the images of this 12, phase 12, so let's see, there are 10 planes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So for each plane, we have a bounding box and that is annotated with its XY coordinates as well as heights and widths. So this is inside our data sets. Now we know our data set. Let's move to the algorithm. Okay. So here actually till here, I'm just showing what is inside our data set. Right? These are bounding boxes. I've plotted only that. And this is the image we have. Like we have just referred using file structure, and now this is referred using Python code. Till here, I've covered only this. Now there is an algorithm which is called selective search. And this is actually an exhaustive technique. Exhaustive means it searches the complete image with many sizes of bounding boxes, right, to see, right, where is the object. So to see where is the object is really actually a very rigorous mathematical concept where we look for optimal solution. Those kinds of things happen in here, right? So first we will understand what is selective search. So one line we see that selective search method is used to generate reason proposals. So reason proposals are actually bounding boxes. So we will refer this kind of thing later just to after understanding the concepts. Right? So here the training was going on. Some I think we will refer this after a few minutes to understand the concept. So the techniques which we have in object detection field are RCNN, reason-based CNN, fast RCNN, faster RCNN, and also there are hog transforms, right? And other than that, we have YOLO. YOLO is very popular and very powerful algorithm because its inference time is very less. In very less time, it is able to produce the results. Training might be large, but inference is very less, right? RCNN is the very basic concept on which the other concepts are developed. So in this webinar, I'm going to cover RCNN and very basic concepts of how this object detection works. Then in the later sessions, we will see what are the few changes have been done to RCNN to make it fast RCNN as well as faster RCNN, and what is the concept of YOLO algorithm? You only look once, right? The version of YOLO 7 has come recently, but most of the people are now comfortable with YOLO 6. So we'll see in the later coming sections on which version we are going to do the hands-on with YOLO. Right. So let's focus on RCNN and the other techniques in this series, fast RCNN and faster RCNN in this session. Right. So RCNN is actually came in 2014 and the paper is called Rich Feature Hierarchies for Accurate Object Detection and Semantic Segmentation. Right. So this paper actually got 9,000 citations within 5 years. So you can see it is very popular because it is able to see and it is able to draw what is inside the image by drawing a bounding box around it and also classifying the objects. Right. And let's see how the selective search works. So first we will see RCNN algorithm, and the basic thing inside RCNN algorithm is selective search and non-maximum suppression, that is IOU or intersection of union. With these two concepts, and a bit of classification networks, right? So let's see the complete agenda. So first we build an object detection data set using selective search. So I've already like shown you the data set inside with that we have images and as well as the proposals. If there are 10 planes, then we have 10 different bounding boxes in our training data set, right? Then what we do is to fine tune a classification network. This we prepare just aside, prepare it, and we'll take it aside. We fine tune a classification network for object detection tasks. We can pick any network, any machine learning or deep learning architecture. Right. In some places, people have used SVM, some have used VGG19, some has used ResNet. Right. You can take any architecture which you can fine tune for object detection task. It means like for the last layer, we have to do the fine tuning. Right. So we will see in our notebook how this can be done. And then there is a major portion comes which we create an object detection inference script that utilizes selective search to propose reasons that could contain an object that we would like to detect, right? Then it utilizes selective search algorithms to propose the reasons. Reasons means that rectangular boxes, right? And then we use some fine tune, then use our fine tune network to classify each reason proposed with selective search. Then we will use this recipe we have kept aside on the selective search proposals to classify each reason, right? After that, we'll apply maxima suppression to suppress the weak and overlapping bounding boxes. And then we get the final results. So let's see the selective search in detail. So selective search algorithm actually generate initial sub-segmentation of input image using a method described by Palenswap a bit up to this author et al. In his paper, Efficient Graph-Based Image Segmentation, right? So what happens in here, sub-segmentation means, what is the meaning of sub-segmentation? So we will see this by an image. I've taken it from the paper. So this is the image and we have sub-segmentation of this input image in this format. There are some reasons highlighted and those reasons have similar kind of textures or colors or fills. This happens on the basis of uh, 4 or 5 mathematical formulations like I've told you that can be color or a texture, right? So with the help of this, does this sub-segmentation of input image. And later it recursively combines the smaller similar regions. What is the meaning of similar? I've already told you, means the regions which are similar in texture, which are similar in color, right? And other things are already covered in here. So like into a larger ones using a greedy algorithm. What is the meaning of greedy algorithm? Like once it will see the region similar to this, it will merge. Then the region next to similar to it, it will merge. Right? Greedy algorithm is like a local algorithm which works in the local regions and make their segmentation bigger after each recursion, right? So this kind of thing happens. The input image, we got the initial sub-segmentation, right? After few iterations, we reach here, and after many iterations, we reach here. This kind of thing generates after doing this greedy alpha, applying this segmentation as well as the greedy algorithm to see the similar regions nearby. Later, what happens? It used the segmentation region proposals to generate candidate object locations. So this is what we are, this is where we are getting the boundaries, or we can say rectangular boxes out of this segmentation regions. This kind of things happens in here. We have reached till here, and during each iterations, we were getting this kind of stuff. So now the similarity score in step 2 in this step is calculated based on the color, size, texture, and fill similarity. These are the 4 basic concepts, and those are formulated using mathematical formulations. And using that, the similar regions are searched by this selective search algorithm to combine that into a larger ones. And that reasons will later convert it into the boxes. So selective search provides 2 variations in the approach. One is called fast selective search and one is quality selective search. So fast selective search is a bit faster during its inference time, and quality selective search takes a lot more time, right? Like faster means it takes fast selective search takes around 9 to 15 seconds when it runs on real images, real time data, real time camera feed. So for real time camera feed, if it takes 10 or 15 seconds, still it is more. So there are other researches happened after RCNN or past RCNN, and we are reached to YOLO Tilliard. So that takes very less time, right? Because it is applicable for real-time object detection. Let's see what is non-maximum suppression, right? Yeah. Non-maximum separation here, before non-maximum separation, after selective search, what we do is to fine-tune region features, which are, we have taken the regions in the image. Now those regions are extracted, like cropped from the image, if you can imagine it like that. And that cropped region only passed through a tuned VGG19, or you can say ResNet network to extract for the classification task, right? Extract the features, and further those features are used for classification tasks, whether it is an aeroplane or it is a dog or a cat, because the model is already trained on ImageNet dataset, so it has seen already 1,000 categories. Now it can work on, if I'm taking here a customized dataset, then it will be able to pick 2 or 3 categories. Then that classification task can be done by any fine-tuned network. So I've taken here VGG19. At some places you will find that SVM is used, at some places ResNet is used. So any fine-tuned network can be used in here. Later, what is done is NMS, that is non-maximum suppression, non-maxima suppression. In place of M, there should be A. U and M, there should be A, right? So in here, the input is a list of proposal boxes B, corresponding confidence scores and overlap threshold. Like if the overlapping of the reasons is that much, then we will allow, otherwise we will discard. So this kind of thing in here. So you can see around this car, we have 3 bounding boxes. And then with the help of this IOU intersection of union concept, we are able to get a single bounding box around the image, around the object, right? So this is actually intersection, and in the denominator, we have union of the proposal candidates, bounding boxes, its areas, right? So this is non-maximum suppression. Let's go back to our Colab notebook. So here we will see how the selective search can be implemented. So this is actually using a computer vision extended version, and the extended version only we will get this is XIMG proc. And inside this, there is a segmentation. Inside it, we have this method, creative selective search segmentation. So I have also taken the reference of the original, like official documentation of OpenCV. I'll show you that also, where these methods are available and what are the inputs and output of these methods. Okay. So here we have this CV XM Ring proc segmentation selective search like strategy, and inside this we have, I'm using this. So inside this we have that create segmentation method. So we use these methods. Maybe it is inside some other class. So create selective search segmentation. We use this method, and with the help of this, we further process our image. And here I'm using this switch to selective search fast, this method, and for faster selective search, right? Then this is the line which actually able to produce all the bounding boxes, right? And this rex is actually rectangular, which is capturing the rectangular shape with X, Y, H, and W values, right? So when we plot all of this, enumerating all the boxes, right? And I've created a copy of our image with I'm out, and here I've plotted this. So this is the plot we got, right? So in the image we can see multiple boxes. Now we will apply the greedy algorithm as well as non-maximum suppression with classification. So here the function is created for this generating the IOU score. So intersection upon union is calculated in here. And again, this creative select, there is no need of this. You can skip this step. This is written again in here. We can directly take this object, which is calculated in, which is actually computed in here, right? And here, what is done is actually trying to see that we do not cross the 2000 maximum bounding boxes which are allowed by selective search algorithms under RCNN. R2000 bounding boxes are allowed because they are actually trying with many boxes, smaller and larger sizes. So in an image, if with every pixel and overlapping boxes we will try. So there can be thousands of boxes possible inside the image, right? That not the final box, that is actually are taking the reasons which are calculated by this exhaustive search. So it is actually capping that we get 2000 and just less than that bounding boxes available, then only we will calculate the IOU of those boxes, right? So IOU is calculated in here, and the labels etc are attached, training images and their labels are appended with our matrices. Here we have declared some blank list in here, and then it is attached, right? So after this, we are getting uh, actually it takes a lot more time to process it, due to which the there is some overflow in the Colab notebook, and it actually utilizes the whole RAM. That's why the um, rest of the cells are not rest of the cells are not properly uh, running, right? We got output till few steps. We can run this algorithm on our computers or on GPUs, then it will perform better, a lot more strong GPU than this Colab. So and means we can only see why how the things are going on, but we might not reach to the final output, right? So here we actually used actually taken the training images as well as labels, and we assigned to two variables. Then we have checked the shape. Okay. Then here what is happening? We are actually importing the model from Keras and some dense layers. And here the VGG19 is used for the classification task. And this is we are getting the VGG19, and we are it's a pre-trained networks. It means we are taking the weights as well with this networks, with this VGG19, right? So this is a model summary for VGG19. Then these are all layers, right? Then here in here we are actually doing the fine tuning. It means the predictions variable is taken, and it actually using the softmax layer, it is applying our input data X, right? Sorry, X new was our data. Let me see once again. I remember it was X new, right? So here X is actually the layers, right? VGG model dot layers -2. It means less than. But we are taking the layers and we are discarding last two layers, right? So that we are taking the layer which is at the second index from last from the end of the list, right? So here the final model is prepared, and then we have used Adam optimizer, right? And then the whole compilation, it means now we are preparing our model for the application. Till here everything is done, like loss and cross entropy loss has been taken, and the optimization is done for the model itself, right? And now till yet we haven't applied our input or prepared data set on this model, right? Till yet only model is prepared, and at the other side our image and annotations and the maximum proposal candidates are taken with their IOUs, right? Then here my label binaries. Then we actually do train test split in here, and then later with image generator we apply this model, right? With this VGG19, right? So as I already told you, I'm not able to run the complete notebook because it is utilizing a lot more RAM in this step, right? It's utilizing a lot more RAM, so because RAM is full, so I'm not able to run the complete thing. I've refreshed the thing again. That's why we are getting less RAM in, right? So I'll share this notebook. You can run on your systems, right? Also the data set. And if there are any issues, you can ping me on LinkedIn or um, on my blog as well. So we can solve the any errors if it comes. So in the next step, after seeing the implementation and basic steps, what happens inside selective search, as well as how to implement this faster CNN. Let's see what is object tracking, right? So this is another concept. My agenda is to cover all the things which are related to object detection or classification or segmentation, right? So one concept after object detection is object tracking. So object tracking is actually tracking a single object in an image. So this is detection and plus tracking the same thing. On every frame, we are tracking this, only this, not this person, nothing else. Where this is multiple object tracking. So here we are tracking multiple cars which are going and coming. So this is the understanding of object tracking and how it is different from object detection. Let's see what is semantic segmentation. So in semantic segmentation, we actually see the reasons. The intermediate. This is the intermediate step we have already seen while understanding object detection, right? Also, there are things like this. So it actually segments the reasons, and this is the intermediate step of object detection, right? So it is actually able to find the not the boundary or the bounding box. It is able to find the complete area where the particular object is located, right? It is able to find out the whole area, because in the bounding box sometimes the object is very small but the bounding box is a bit larger, so we actually do not see the complete boundary of the object. So semantic segmentation covers that shortcomings. Then there is instance segmentation. So this is object detection. We have already seen the examples. This is semantic segmentation. It actually segments the larger portions, whereas instance segmentation is actually this is classifying the images 1, 2, and 3, right, and the four background in 4 classes. Whereas in instance segmentation, every instance is classified like individually. So this is what it is, instance segmentation. And this is another example of that. Many instances of cars are available. Maybe in semantic segmentation, we have everything in the same color. It means they belong to a same class. But here, every instance is different, right? The people is this is the person. We can vaguely see it. So this is actually will be a different thing in semantic segmentation and instance. Everything is having its own class, right, or a label. So in the coming sessions, we will do more hands-on on RCNN. So if the today's session hands-on is not completed particularly, so I'm trying to prepare more notebooks in which I'll do the complete implementation where we reach till the final output. Maybe it's not possible with Colab, so I was also started working on our my Visual Studio code. So I have to download a larger data set. That's why it has taken a lot more time. So thank you for joining this session. There are 15 minutes left. During that time, you can provide your feedback. I'm generating a feedback forming with this Microsoft Teams. So I'll send you the poll or the link so that you provide the feedback, and as well as if there are any questions from your side, you can ask me. And if you are happy with the session, please comment.